It's Friday afternoon, so got to keep the energy up. Good afternoon, everybody. My name is Mike Freeman. I'm a faculty member at the University of Washington. I'm usually more active on Twitter, but feel like in recent times I'm just polluting a generally more important political conversation, so I haven't been as active these weeks, but usually you can find me on Twitter as @MFViz. This afternoon, I'm going to be talking about visualizing concepts. We've talked a lot about visualizing data, seen some great tools for it. But I'll argue that most of the time what we're trying to visualize is a concept. And it is easy to lose touch with what we're trying to do when we're lost in the coolness of the tools. Yesterday, Lucas, you just asked a question. Where'd you go, Lucas? Hey, Lucas. Lucas asked us a question and asked if we all believed that climate change was real. And climate change is an idea, right? Climate change is a concept. And everyone in this particular scientific community seemed to have faith in that concept. But that concept is not something that we have managed to communicate to a general audience. We lost that battle. And in the last few weeks, we lost a lot of other relevant political battles about what sort of consequences there could be given the results of the election. And I'll argue that as a scientifically educated and generally privileged community, we have a lot of important concepts that we need to be thinking about visualizing and communicating to a broad audience in the next few years. Without further ado, move off of my political soapbox and talk more about visualizing concepts and using a particular tool, D3, but won't talk too much about the use of that particular tool. So I'm going to start with a question, and I would actually like you to take 90 seconds. And with the person next to you, preferably if you have a sheet of paper, I want you to answer the question, what is division, as if you were explaining the concept of division to someone who has never heard it before. You're unaware but intelligent audience. So I'll give you 90 seconds and go ahead and explain this to the person next to you. All right, it seems like the conversational vigor is dwindling a little bit. I imagine you all managed to perfectly explain this concept of division. Out of curiosity, how many people started with n number of objects? You have n soccer balls. You have 100 marbles. Very few. How many people started with a pizza? What did you all start with? If not pizza or soccer balls. Maybe I'm used to working with a different audience. An octopus? I'm on the East Coast. This is taking unexpected turns. You don't like soccer balls or pizza out here? So I've asked this question to some courses that I teach a number of times, and trying to think about visualizing concepts. I'll argue that the first thing you need to do this is a data structure. Right? We have an abstract concept, and in order to visualize it, we needed to come up with some amount of data. Right? And once we have a data set, we can operationalize it in a variety of ways. Right? We can choose specific algorithms to do things like, say, change the color of each one of those elements, or we could, say, change the x or y position as well. So in order to explain this generalized concept, we needed to map it to an underlying data structure so that we could visualize it. Right? There's no D3.concept. There's no ggplot.concept. Right? We need to take the responsibility for figuring out which data structures we can leverage in order to explain our concepts. So the thesis of this talk is that in order to visualize concepts, we need to do a few things. We need to isolate specific ideas. We need to identify underlying data structures, and then leverage corresponding algorithms. So I feel it would be inappropriate to not explain this visually, but I'll wait for the two pictures. Don't worry, these slides will be online, and you can take much more high-quality screenshots, though I did find myself taking every picture of one of Jenny Bryan's slides this morning, so I understand. So what would this look like visually? Right? Well, if we have some sort of concept, like division, we can map it to underlying ideas, right? So let's say there are two ideas associated with division. One might be that you have a single element that you're going to break into smaller pieces, like a pizza. Or you might have multiple different elements that you're then going to distribute across n groups. So that would be you have 5 soccer balls and 2 students. How are you going to divide them? I should have picked even numbers. We're going to have a popped soccer ball. So we have different ideas associated with that concept. But in order to show those ideas, we need to generate some data structure. Right? We need to come up with a real data set and identify that, or synthesize it, right? Or simulate it, right? Come up with n numbers of elements. And once you have those data structures, there, of course, are corresponding algorithms that you can use to put them on the screen, right? Regardless of whichever tool you're using, you need to figure out how you're mapping from data features to pixels so that you can communicate this. And of course, in order to draw this, I knew I wanted to draw this diagram because I wasn't using a point-and-click tool and was using D3 instead because I wanted to waste an evening doing something that I could have drawn by hand. I had to come up with a data structure, right? If I wanted to show you all of this, I needed to write this down, right? I needed to identify the appropriate, or in this case, create the appropriate underlying data structure so that I could take what is a nested JSON object, some sort of tree element, and show that in a diagram like this one. So that's one of these pieces of the puzzle, right, is figuring out what those underlying data structures are that are driving your concept or the visual explanation of it. And we're going to walk through a few more of those as we move forward. So we can take a couple sort of other fun ideas like bouncing. People have done the hand-raising thing too much. How many people actually use D3 here? All right. Oh, OK. You're all sort of slow to raise your hands or admit that. I'm not going to ask you a question. Don't worry. D3 has a lot of magic built into it, right? So it does these beautiful animated transitions, and it can apply particular easing functions, right? So you can make something look like it is bouncing, right? And it looks like it's magic, right? There's some sort of magical wizard behind here that can make things bounce up or bounce down, right? This doesn't make any sense. And you sort of use these things out of the box and don't take them for what they are, which is some certain amount of data or some algorithm that you can use to do this. Right, so if you look through the D3 code, because again, you don't have anything to do on a particular evening, you can look through and find what the bouncing algorithm actually is, right? It's these 11 random variables, and then put in this awful nested ternary operator for what this returns, right? I didn't write this, right? I couldn't write this. But what seems like magic is actually finding an appropriate algorithm, and as well as these 11 seemingly arbitrary data points to make something look like a generalized concept like bouncing. But this isn't just about making things bounce or explaining something like division. We can also use these approaches to try and explain more complex concepts. So I'll be teaching an Introduction to Data Science course at the University of Washington. I have a much more robust experience working with visualization than with working like things like statistics. And I'm reading through, and something will say, oh, central limit theorem, this is the foundational part of statistics, but is never actually directly used, right? I don't find myself calculating this or using it in any statistical package. So I wanted to build a visual explanation of this. And the way to do this was to think about what the constituent ideas were that explained the central limit theorem. Because you can get by running a lot of regressions or taking averages and doing inferential statistics without understanding some of these core ideas. So this also started with simulating a data set. So you can use a whole variety of packages. I was using JStat to come up with random distributions. But here I just have 100 elements, and that, of course, has a population mean. And we can do something like take a sample. And as we can see, if we take 10 out of these 100 elements, they might be any 10 collection of folks. And sometimes the sample mean is super close to the population mean. Sometimes it's quite far off, right? Like that time we just about nailed it, but then we take another sample and we're off by quite a bit, right? So how can we ever sample from a population and talk confidently about inferring patterns in that population? And that is what the central limit theorem actually enables us to do. But we need to think about doing things that we don't necessarily do in the real world, like taking multiple samples of a population. So if we start taking multiple samples, on this top bar here, we've got our population, and the population mean is shown. And then we can start keeping track of our sample means and the mean of those means as well. So as we take more and more samples, we can see that we're getting a distribution of means of our samples, and then we can look at the mean of those means. And with some intuition, as I'm clicking this more, you're seeing that the mean of the means tends to move towards this population level mean, right? This is an interesting behavior, but it's also sort of intuitive, right? If you sample more from the population with replacement, you're going to get better ideas each time, but we're moving towards being able to leverage this for inferential statistics, right? And to do that, we need to introduce a few more ideas, like thinking about what the distribution of our population is, and then what the distribution of our sample mean is, or our sampling mean is. So we're going to look at this, the actual distribution of this population. And as you can see, it's not normally distributed. But we need normal distributions to do a lot of explanation and inferential statistics. We'll get there, though. So if we've got this population mean, if we just take one sample, it looks wonderfully normally distributed. But that's more about how this line tends to be drawn. But as we take more and more samples, we're seeing that the mean of our means, right, the sampling distribution of the mean, is not in the same distributional shape as our population mean. And this is important, right? We're starting to approximate a normal distribution. And if we do this over and over again, I don't want to stand up here and click this over and over again. But if I buy some time and just sort of watch this grow, we're starting to approximate a normal distribution, right? And when our distributions are normal, we can start to make inferences about the population, right? If we take a random mean, well, if we know the size of that population, then we can think about how far off it is, and we can generate things like confidence intervals, right? This is extraordinarily powerful to being able to talk about how certain you are about what your guess is. And to slide back into moderately political ranting, a lack of communication about confidence intervals has made a lot of people rather upset in the last few weeks when it came to things like election predictions. But not a lot of folks have taken the time to walk through and try and understand these things, nonetheless communicate about the uncertainty in their models, which is something that I would urge all of you statistical folks to do. So if we keep repeating samples, we can see that we get closer and closer to the actual population mean. We're approximating whatever the truth is. We luckily know that here because we have our entire population. And finally, we can get down to an overly verbose definition of the central limit theorem that you can grab from Wikipedia. But this means that we can understand the probability of a population mean given an observed sample mean. Right? We can guess what the distance is between the sample that we drew and the actual capital T true mean of that population because we understand the distribution of the sampling means, right? The distribution of the sample means. So this is explaining why a lot of the inferential statistics, why our p-values pop out magically, and why we can start to talk with confidence about an expected range of values pops out. So in order to do this, to explain this concept, it involved a few things, right? It involved creating synthetic data and sampling out of that data. But it also meant taking this concept and breaking it down into a variety of constituent ideas, right? Like introducing slowly, and this is following a lot of the storytelling tools that people have talked about throughout the conference, is putting this out into a process that people can understand and actually confront one component at a time, right? Before trying to understand this full idea, you sort of allow someone to interact and do things like take a single sample up above before you start talking about a mean of sample means, which doesn't resonate intuitively with a lot of people, myself included. So that was my a non-statistician's approach to explaining the central limit theorem, right? A concept that we can use to understand a lot of our statistical approaches. Let's take something a little bit less dense for those of you who I lost in between division and now. Let's just talk about gooiness. I love this. It was made by a visualization designer and developer named Nadi Bremer. I think that she is doing some of the best visualization work, period. And this is sort of a fun side project of hers. If you don't know who she is, if you ever want to feel bad about yourself, go look at some of the work that she's done, because it is truly, truly extraordinary. And I saw this and I recognized that hexagons are hip. They're all over the Plotly stuff. All these stickers are hexagons. I don't know why they're so cool. I love them. They tessellate. I guess that's cool. But they're sort of popping up all over the place. But I'm watching this, and it has to be magic, right? She has found the magic function and can just make things look gooey. But of course, that's not entirely true. While she's extraordinarily talented, there's no magic behind this, right? There's data behind this. There are data and algorithms that are driving this. And they're pretty gross. These are adopted from a GUI tutorial that she links to. But in particular, it is defining two things, right? One is adding a blurring effect. So when two elements are close to one another, they are sort of blurred. The surrounding pixels around them are blurred. And that is done in this FE Gaussian blur up here with a certain standard deviation. And then there's an applied color matrix to increase contrast. So if you have slightly blurred areas that are overlapping one another and you really heighten the contrast, it will create that sort of goopy blob blur effect. And to do that, she had to write out this matrix of particular values. Now, have I taken the time to understand what all of those are? No. Right. I spend too much time doing this, but I don't have that much free time to look into these things. But this is really about finding a data structure that can express a concept that's sort of abstract, like gooiness. And we're all glad that she did, right? And she made some really cool ones that were like hitting golf balls with these. It actually helped to explain a concept like what it looks like to thwack a golf ball, right? And this effect actually really helped explain some concepts underlying in physics. But this is also just a fun way of looking at it. Bending. After last, almost 2 weeks ago now, I found myself in need of some inspiration and saw a Martin Luther King quote that I really liked, which was this one, that the arc of the moral universe is long, but it bends towards justice. I heard this resonating a lot, and I wanted to create some visual representation of this, right? So I had this idea of bending. I wanted to show bending. So of course I Googled like how to make text bend D3, because that's how all D3 projects start, is Googling someone else who's done it before. It turns out that if you want to draw an SVG, you just have to manipulate different data points, right? So there are a variety of different ways that you could think about bending. This is using a quadratic approach to bending a path, and luckily it's really easy to draw text on top of that path. But I wanted to build, I sort of kept finding myself fiddling and changing one parameter and then changing another. So I decided just to add some controls here where I could change the distance between any two x points, and you can see that those vary quite dramatically. We can just set that to 400. And you can also pull it up and down in the y direction by setting a different anchor point, sort of higher vertically or lower from your continuum, right? So we could set that also to 400, and we get a higher bend, right? This idea of bending is exaggerated when we change that underlying data set. And then I did silly things like change how far off we wanted that path to be. That sort of looks like I'm crossing it out. It was just the opposite, right? I wanted to put it down a little bit further, separate it from the text, and maybe I wanted to switch the way that I started this quote, right? To think about whether or not things are coming up or if they're going down. There are a lot of sort of sentiments that you get out of this. And I built a little tool to do this so that you could do things like download the SVG that you get out of it. So if you have any text that you really want on a curve saved in an SVG file, you can just click SVG, and then if you look at that, you'll have your SVG file, which is cool for a reason that I'll show you in a moment. But to do this, it was really about finding the right algorithm for doing that, right? Finding the associated data points for the anchors for how I wanted to pull this curve, and then also stringing them together into a long path. So if you've ever worked with SVGs, which I hadn't really, you start and you end up just getting some long string of characters essentially. But to do this, we had x and y start points, and then just looping through however far, however wide your page was, and setting different x and y anchor, sort of set points, and then pulling them up or down in between each one of those. And then you can just add it to the page like you would anything else with D3. But there one reason that I thought that this is really cool, the reason it's valuable to export to an SVG is if you know anybody that has a laser etching machine, you can just give them an SVG, and then there's this awkward point where they're like, how did you make this? And you're like, oh, I built a website, and they're like, oh, but I need to change this little thing. It's like, oh, but I didn't do it in Illustrator. But you can basically spit it into a laser etcher and make some nice art and try and make the world a slightly more cheerful or inspiring place with what you've made. So fun to move that off of the screen. One more concept that I want to talk about, this comes from a man of many trades named Jim Vallandingham, who works for a company called Boku, who has an awesome conference called OpenVizConf. And Irene, I'll embarrass you. You probably won't even raise your hand, but there you missed it though. If you have questions about that conference, it is an extraordinary conference, and applications to speak are due this Sunday. So if you are interested in speaking there, you don't need to know Irene and bother her with questions. You should just go online and fill out the application. But enough about OpenViz. This is about a project that Jim did a few years ago called Visualizing the Racial Divide. And I think this is extraordinary. And every time I see it, it has a profound emotional effect on me. And I think that's a lot of what we're aiming for, right? People don't often remember the numbers that you show them or what you're trying to tell them, but they remember how they feel, right? And if you're trying to visualize a concept like segregation, I don't need to know the Gini coefficient of a variety of different cities. I can get a feeling of what that looks like. And what Jim has done here is take the proportion of people that are white and not white in each city, which admittedly is a limiting view of thinking about race, and shading each one of those census tracts by the proportion of white versus non-white population. And then has done this interesting thing, right? We've all seen sort of the choropleth style map that looks like this, but Jim has reinterpreted this as a network, right? Where each one of these census tracts is a node in the network, and the attraction or repulsion between them is driven by the racial similarity. And the consequence of this, when you take a really racially segregated city like Baltimore that Peter was showing the other day, you get a sense of how disparate these geographically adjacent census tracts might be in reality. It was a little bit heavy-handed, not necessarily the case, but gives you a really interesting sense of what some of these places are like Denver, where I grew up, which was an extraordinarily white city. Or you can look at other cities like Chicago, which are highly, highly segregated. And this visual use of space, right, to separate things out, it can be quite jarring, right, because we're not used to seeing a map break apart. But I think the use of visual distance helps communicate an idea of a different lived experience across these different areas, which I thought was quite interesting and quite moving. So you start with something like a variety of census tracts, and then you can apply the underlying data set, and you can shade each one of these census tracts. But again, this was understood as a network, right? So this is a network diagram across these. And you can imagine drawing those as the initial start positions, and then the attraction and repulsion is driven by racial similarity across two adjacent census tracts, which is why we get that effect of certain areas clustering together and other ones pushing apart. That is pretty much what I have for you. Here is a link to what has been included. These slides themselves are up. They're just a website, another thing that I won't be doing again. I'll put these in the Slack channel or anywhere else. The code that I used to make the slides is there, and then the handful of examples that have been included. It's like this is getting a handful of more pictures, but my next slide just says thanks and has my Twitter handle. This seems a little bit more useful. So I'll just encourage people to think about the important social concepts that they're trying to visualize as they move through this process of identifying ideas and data structures, and say thanks and open for a few minutes of questions. Does anybody have any questions?
Sorry, I actually was kind of impressed by that, the map.
Yeah, let's just go back to that because it's amazing.
And something that kind of resonated with me is the idea that people don't remember the numbers, they remember
Yeah, you got a microphone so other folks can hear you as well.
Something that resonated with me is like people don't remember the numbers that they read, but they remember how they feel. Do you know of any other like good examples of that, or?
Yeah, I'd say my other really driving one, if you look at guns.periscopic.com, this is a really extraordinary visualization of gun deaths in the United States. I've probably watched this hundreds of times, and I couldn't tell you any of the numbers that are there, but you get to see these people who had a trajectory in their life and were killed at a certain point, and you see the number of years of life that are lost. This is using a really powerful structure where it's individualizing the data, so you get to see that each one of these lines is actually a person before you start to draw all of the lines on the screen, the number of which is terrifying. So I would say that this is another example of you remember, I don't remember the numbers, but I certainly remember how I feel about gun control in the United States, which is not different from how I felt before I saw this, but that might not be true for everybody else. Yeah, another question.
So thank you for the great talk. This figure that you showed, especially in the beginning of the hierarchy, really spoke to me of like some ideas of like ontologies and ways of grouping these ideas together. Can you talk about moving forward? Is that a kind of structure maybe contrasted or similar to Google's knowledge graph that would be worth building out to aggregate all of these ways of representing different concepts?
So you're talking about like the idea of having a concept and breaking into ideas and ideas into data structures and data structures into algorithms. So that is something that I think people do really implicitly. You are often handed or already have a data set in mind. And I'm not saying that you should alter the data to try and get your point across, but you should expose the data in a way that it shows the true information that's there, right? I don't have personal plans to really extend that, but I think that has helped me really move through what my process is of like, if this is an area that I'm interested in, here's how I'll go about moving forward in it. But thanks. Any other questions? I think we have a couple more minutes. Also, if you don't, that's just fine by me. Yeah, I've got a question right behind the microphone.
Not a question. I just want to make sure everybody knew about your tutorials online.
I'm sorry?
I wanted to make sure everybody knew about your tutorials online.
Oh, yeah. So I teach at the university. I'll put this in the Slack channel as well. Teach at the University of Washington. One of the courses that I teach, it boils down to intro to using R, and I have a bunch of different learning modules on different topics. So if you're someone who's getting started with R or want to teach others, there are other, like DataCamp I think is really great, and there are a bunch of tutorials online. But I've gone ahead and in each one of these, here's my long way of describing dplyr, and I say that I took these from Strata NYC, a lot of these pictures. But I also have exercises in here where there are master branches and complete branches that have the uncompleted and completed version of the code. If you're trying to learn something like dplyr or Shiny, or if you're just getting started with R as well. But yeah, thanks again. Anything else? One more question. I'll be around the rest of the day. So thanks very much for your attention, and I'll see you around. Have a good rest of the day.